my analysis of the Metropolis-Hastings algorithm and MCM algorithm, and my name is Michael Green. The Metropolis algorithm was first introduced in a 1953 article titled Equation of State Calculations by Fast Computing Machines. The algorithm was created to simplify Markov chain Monte Carlo methods or experiments. So Monte Carlo experiments, they're a broad class of computational algorithms that rely on repeated random sampling to obtain numerical results. Monte Carlo is similar to a city back in the day, similar to like Las Vegas, as you can see in this photo, where people were trying to predict the outcome of different types of games that had different systems of equations that gave a probability distribution. And as people tried to predict more and more complicated things, what was found was that a lot of them had had very hard difficulty normalizing the distributions, and it made it often difficult to predict. The Metropolis algorithm was instead proposing to choose a more simple function that had the same probability as the system you wanted to predict, and then using an iterative method, so you'd iterate through step by step, using the simpler function and the previous result to either accept or reject the current iteration. And so what was found was that there was a statistical prediction showed improved convergence onto the actual results. So the original author actually has a bit of controversy as to who deserves credit. Without getting into too much detail there were 5 original authors here. So Nicholas Metropolis, the Rosenbluths, Ariana and Marshall, and Augusta and Edward Teller. So obviously the naming of the algorithm was given credit to Nicholas Metropolis. However, 40 years later, the Rosenbluths claimed that the majority of work was actually done by them. And then obviously the name of the algorithm is actually the Metropolis-Hastings algorithm, and that is because another man known as K. Hastings came onto the scene later in the 70s and contributed additional findings to the algorithm. So here is his photo. So the importance of this algorithm, a scientist named F. Sullivan, who was studying the Metropolis-Hastings algorithm, said that the Metropolis algorithm began as a technique for attacking specific problems in numerical simulations. Later, the subject exploded as the scope of applications broadened in many surprising directions, including function minimization, computational geometry, and combinational counting. Today, topics related to the Metropolis algorithm constitute an entire field of computational science, supported by a deep theory and having applications ranging from physical simulations to the foundations of computational complexity. So, because it can be a little bit difficult to articulate the applications of this algorithm, I wanted to use this video by Ben Lambert as a visual example. So, in this video, you can see he's using a 3D render of a cow as his probability density. Here's a picture of this blue cow is showing the probability density. So what he's doing is he's using a function which is defined as e to the minus 100d, where d is the perpendicular distance from the current point we're iterating to the next to the nearest exterior of the cow. And so he's about to run 6,000 iterations of this function. And as you can see, the ones that the function is accepting pretty quickly start to resemble the actual exterior of the cow. So this shows how sampling from the Metropolis distribution can work with a distribution that is extremely hard to normalize, like the exterior of a cow. Since that example is a little bit silly, here's more of a practical example that's pretty common. So when you find a mountain range, scientists want to predict the runoff of a mountain range, and here is the actual density representation of the runoff and the slope of each of these mountain ranges. And they can use the Metropolis-Hastings algorithm to predict and give pretty accurate samplings of what to expect year in and year out as they get more data. And so here's the Metropolis algorithm and how closely it can represent the slope of those mountains after 4,500 iterations. Here's a quick analysis that was given from the original authors. Essentially, what they say here, so they were trying to predict some different thermodynamic particles. They were running experiments for several hours. And so For computing time of a few hours with presently available electronic computers, it seems possible to obtain the pressure for a given volume and temperature to an accuracy of only a few percent. Obviously, the algorithm has grown immensely now. Here was the original computer that they were testing it on, known as the Maniac 1. And so obviously the authors would be amazed to see just how far their algorithm has come. And here is my sources cited. Thank you for watching.